Okay, so today we go for the starting of second unit. That is nothing but implementation of discrete time systems. In the last lecture, we have completed the unit one, and today you are having the one quiz test on unit for the unit one. I already sent the message through Moodle few days back. You may be getting the message, and related with some few instructions are there that I will share with you at the end of this lecture, because we are not able to conduct the test on the Moodle, as at present the limitations of the students are 100 only. So as I have to conduct this test common for EC and CSE class, I will find out some alternate solution. So I will share that with you, and at 1:30 you have to give the test. Okay. And one more query I'm getting from your students, that is submission of the experiments. So again, Moodle having the one issue is related to the students' strength, means it is not allowing more than 100 students per at a time. Another issue we are getting is the size. At present, our Moodle is full with the storage capacity. So we are doing to increase the Moodle size, storage size, by purchasing some extra license for that. So just a second. Now I am audible, Ekta? Okay. So in Moodle, as the storage capacity will increase, and as you complete the practicals, as EC students are completed, by next week I will share the uploading link for your practicals, for practical 3rd and practical 4. Yeah, regarding the test, as we are not able to conduct the test on the Moodle at present, because at a time we cannot assign the test to more than 100 students. So if I club the EC and CSE both class, the size of the class will increase more than 100. Total around 114 students are there. So instead of conducting that test on Moodle, today I will conduct the test on one another alternate. So I will share the details at the end of this lecture. Okay, so let us start with the unit 2. So unit 2 is implementation of discrete time systems. So as discussed, the discrete time system has finite or infinite impulse responses. So if we classify the discrete time system, it is having the two types. Either it is having the finite impulse response, or it is having the infinite impulse response. So in short, it is known as a FIR system or IR system, or FIR filter or IR filter. So this is known as a type of the discrete system. So here the word we are using is a type. Then how we implement that particular system, or that particular system is known as a form of its implementation. Form of its implementation means which type of structure we are using for the implementation. And what is the meaning of structure is, the structure is nothing but a block diagram or a signal flow diagram that consists delay elements, adders and multiplier. So the structure is nothing but we represent the FIR equation or IR equation in a block diagram representation or in a signal flow diagram representation, which consists of the three main elements, that is delay element, adders and multipliers. So different filter structure dictate different design strategies. So what is the difference between these structures are? So they are proposing the different design strategies and in the same equation in different forms. So if we arrange the same equation in different form, it will provide you the different structures. So these are the main things. First is the type of the filter, that is either FIR or IR filter. First we start with the FIR filter, then we go for the implementation of the IR filter. Then form of implementation means structures. So in this chapter you have to study about various structures. So structures are nothing but how you are implementing that particular equation of FIR or IR filter that give you different design strategies. So here we will study about the different structures, which are nothing but different design strategies. So that meaning of that is arrange the same equation in different forms. So only we have to arrange the same equation, means whatever FIR equation or IR equation, we have to implement that equation in a different forms. So we obtain the different design strategies. So these are the introductory points. Now parameters for selecting the structure. So now for implementing the structure or selecting the structure, what are the parameters? So here we define the LTI system is characterized by the linear constant coefficient difference equation. So LTI full form is linear time invariant system, characterized by linear constant coefficient difference equation in time domain. So if I represent the LTI system with this linear constant coefficient difference equation, then it is given by the equation y of n is equal to sigma k is equal to 1 to n, here minus sign is there, k is equal to 1 to n ak y n minus k plus sigma k is equal to 0 to m bk x n minus k, where ak and bk are constant coefficients. Same thing if I represent in the z domain, I am getting the filter response or transfer function, that is h of z, that is nothing but y of z divided by x of z. So in the numerator you are getting the term sigma k is equal to 0 to m bk z raised to minus k. In the denominator the term is 1 minus sigma k is equal to 1 to n ak z raised to minus k. This is the equation in the time domain, you can say. Here I am representing the same equation with the transfer function in z domain. Okay, so prior to discussing all, let me ask you one question. What do you mean by LTI system? Okay, how many of you are aware with the term LTI or linear time invariant? Just say comment, say yes in the comment box only. No need to write the answer in the comment box. Those are knowing the answer of LTI, please comment. Rishabh told me the answer. Yes, okay. Rishabh, please give me the answer.
So what about some first linear system? Because in linear system we have two there are two main properties that linear system should show. First is homogeneity and second is additivity. Homogeneity relates to if input signal is um, gain some amplitude, some amount of amplitude, then output result should gain the same amount of amplitude. That's what we call homogeneity property of a signal. And the second is additivity. Let's suppose we have give two separate signals irrespective of each other, and we get two separate outputs. If we give addition of their inputs, the addition of these inputs, then we should get the addition of their responses when we give them individually. So that's we call additivity.
Yeah, combining both, this is the correct answer. Yeah, Rishabh. So the exact answer is, when we say linear system means it fulfill the two requirements. It will fulfill the property of you can say additivity or superposition. Another it fulfill the property of homogeneity. So if I am applying x1 and x1n and x2n separately, and whatever output I am getting y1 and y2n, so if I am adding the signal x1n and x2n, and whatever output I am getting, that is must be the same as their combined output. So in that case you can say that property is superposition or additive property. Second one is the homogeneity. Suppose I scale the input systems x1 and x2 by some scaling factor a. So I am writing a of x1n and a of x2n. So what happen at the output, whatever response I am getting, that must be scaled by the same value or same factor a. So in that case you can say that system is fulfilling the property of homogeneity. So when any system fulfill these two properties, what happen when you go for the plotting of curve, you are getting the straight line. Why straight line? Because it fulfill these two properties. So as your input is increased, in the proportionate amount your output is increased. So always there is a proportionality between input and output. Okay, so that kind of systems are known as a linear system. Okay, time invariant, I think you all of you are knowing about the term time invariant. It doesn't depend on any of the particular time. So if you vary the time of that particular system, again you are getting the same output. So that is a time independent or time invariant type of system. So this is the full form of LTI system. Okay, so again we come with the start with this. LTI system is characterized by this equation. So this equation we are using in the time domain, same representation I have shown in the transfer function. H of z is equal to y of z and x of z, and this particular equation. Okay, so here parameters for selecting the structure are, which is the ratio of two polynomials in z inverse. So whatever here we are getting, these are nothing but the transfer function, which is nothing but the ratio of two polynomial in z raised to minus 1 or z raised to minus k in general. We obtain the zeros and poles of the system function, which depend on the choice of the system parameters, that is parameters or coefficients ak and bk. which determine the frequency response characteristic of the system. So here whatever parameters we are selecting, AK and BK, so this will define the frequency response characteristic of that particular system. Okay, now here the choice of structure for realizing the LTI system depend on the following criteria. So when you select any structure, so again for the selection of structure, here are the three main criteria. First one is the computational complexity, as we have calculated in DFT and FFT. So here same thing we apply, but here one more thing is added. Number of additions we have to calculate, number of multiplication, and delay elements. So these three parameters we have to calculate and compare that which structure we have to select based on the number of addition, number of multiplication, and number of delay elements required. Second is the memory requirement. Number of memory locations required to store the coefficient values and past input and past outputs. Past inputs and outputs only. So based on your storage requirement, some structure required less memory, some structure require higher memory. So these are based on what? These are based on the number of memory location required to store the coefficient values. First, whatever coefficient you are taking, AK and BK, so these coefficient values and their past inputs and whatever output you are getting, and also some memory is required for fetching and execution. So all this we have to calculate. So that is nothing but our memory requirement of that particular structure. Then finite word length effects, so that is a finite precision effects. So depend on amount of precision required. Okay, so depend on the amount of precision required. As you increase the precision, what happen? Your word length, you are require the higher word length. But if you reduce that, you are getting the some errors due to that limitation. So that is known as a quantization or rounding of error. So that is known as a finite precision effect. So if you are defining, we don't go for the infinite precision. We have to limit our range of bits or length of the word. So due to that, whatever errors you are getting, that is known as a finite precision effects. So depend on the amount of precision required. So if I am applying the 6-bit for the calculation, and if I am applying the 7-bit for the calculation, the thing is in 7-bit compared to the previous lower number of bits, I am getting the higher precision. So that is known as a finite word length effects or finite precision effects. So these three parameters or criteria we have to consider when we select any structure. Okay, so we start with the first structure. Prior to starting, just a second, let me show you these three main elements which are easy to understand. Adder, here x1n is input, x2 is given as input. This is your adder or summer circuit. Here both our inputs are added and you are getting output is x1n plus x2n. Then second is the multiplier, or another word we are using is gain. So x1, it is passing from this line where the gain coefficient is shown a. So here you are getting a of xn. So here you can say y of n is nothing but is equal to a of xn. So whatever the gain or whatever the multiplier, it multiplied with that value and you are getting the output. Last one is the delay element or shift or memory. So here x of n will pass from this delay element, that is z inverse. So what happen when you apply the z inverse, it is delayed by 1. Here if I am using the z raised to minus 2, here you are getting x of n minus 2. Okay, so this is nothing but the three elements we are using for the implementation of LTI structure. So whatever structure we will learn for this particular chapter, in that these three elements are only used: adder, multiplier, and delay elements. Okay, so we start with the first one, that is a FIR system structures, and in that we go for the direct implementation. So first we start with the FIR system, finite impulse response. So the transfer function for this FIR filter is given as h of z is equal to b0 plus b1 z inverse up to bm minus 1 into z raised to 1 minus m is equal to sigma k is equal to 0 to m minus 1 bk into z raised to minus k. The same thing can be represented in the difference equation form. In previous slide, here we written difference equation first, and then we return the h of z, or you can say transfer function. But here I am writing the transfer function first, and then I am writing the difference equation. You can change there, nothing but here we are representing in the frequency domain and in time domain. So h of z is given by this equation: sigma k is equal to 0 to m minus 1 bk into z raised to minus 1 or you can represent same thing with the help of difference equation, that is y of n, that is sigma k is equal to 0 to m bk x n minus k. If you expand this equation, the terms are b0 xn plus b1 xn minus 1 plus up to bm minus 1 into xn minus m plus 1, which is a linear convolution of finite support. Here whatever we are doing, that is nothing but we are performing the linear convolution in time domain with finite support, because our range is finite over here, so we can say that linear convolution of finite support. Okay, so the impulse response of the FIR system is identical to the coefficient. Here as we have seen that here h of z having the coefficient b0, b1 and up to bm minus 1. So here what we are writing here, whatever impulse response we are getting of the FIR system is identical to the coefficients bk. So what happened? So h of n is nothing but same as b of n for the values of 0 to m minus 1. For the remaining values it is 0. So now we can say h of n is same as b of n. So in this, whatever b0 coefficient we need, that coefficients are provided by that particular filter. So this is nothing but the impulse response of this particular filter, that is h of n terms are same as b of n for the range 0 to m minus 1. For the other values it is 0. Okay, now the two terms based on this value m minus 1. So when we say what is the order of the filter, so the order of the filter is nothing but it represent the value m minus 1. So whatever this m minus 1 term is mentioned over here, it represents the order of that particular filter, and whatever term m we are using, that is nothing but the length of that particular filter. So when anybody tell you to calculate the order of the filter, you have to find out the value m minus 1, and what is the length of that particular filter, that is nothing but the value of m itself. Okay, so this is how we define the order and length of the filter. Okay, so now we go for the first structure, that is a very simple to implement, means whatever equation we have learned, this equation we are implementing without any modification. Okay, so whatever the equation, h of z is equal to sigma k is equal to 0 to m minus 1 bk into z raised to minus n, and as we have seen, this b coefficients are same as h coefficient, so here we can write hk into z raised to minus z. Okay, so we are implementing this equation without any modification. So when you are implementing equation as it is in the block diagram or signal program, that particular arrangement or structure is known as a direct form implementation, because we are not doing any manipulation in the equation, we are directly implementing that equation. So here direct form structure is shown. So the difference equation is implemented as stepped delay line, since there are no feedback paths. As you have seen that in FIR filter we are having only the numerator part, no denominator part is there. So here no feedback paths are shown. So note that since the denominator is equal to unity, there is only one direct form structure. So in this FIR form only numerator is present, and for the denominator you are having value is equal to 1. So in this case what happened, whatever filter design you are getting, it is having only one direct form structure. So that's why it is known as a direct form structure only. But when we will study about the IIR filter, as numerator and denominator both parts are available, so either we implement numerator first and then denominator, or we change it to first denominator then numerator. So based on that the two types will occur, that is direct form 1 or direct form 2 structure. Direct form 1 means you are designing structure in such a way that your numerator part appear first and then denominator parts. Another in the direct form 2, your denominator part appear first and then numerator. But here as only we are having the numerator part, no denominator part is exist, as it is having value unity in the denominator, we can say that it is having only one direct form structure for the FIR filter. Okay, so here as we have seen this equation, just a second, let me bring this equation over here. Okay, now we are implementing this particular equation. H of z is equal to b0 b1 z inverse plus bm minus 1 into z raised to 1 minus m, or in general sigma k is equal to 0 to m minus 1 into bk z raised to minus m. Okay, so here we have to implement this structure or this equation, but as we have discussed, these zero coefficients are same as h coefficients of the filter. So here instead of b0 term in the structure, we have used the terms h0, h1 like this. Okay, so we first term is h0, so x of n multiplied with h0 and then given to the header. Second term is h1 having the delay or 1 unit delay, or you can say it is multiplied with z inverse. So x of n multiplied with z inverse. So here you are getting the term that is x, just a second, here you are getting the term that is x n minus 1, because here 1 unit delay you are applying. Then again it is multiplied with b1 or h1 term and then added. So here you are applying the first term, this is your second term, and then third term is you are applying the 2 unit delay. So at this particular occasion you are getting the x of n minus 2 term, which is multiplied with h2 and again added. So this is nothing but the direct form implementation of the equation. So this is up to the h of m minus n values, m minus 1 values, and you are getting the y of n at the end. Okay, so this is nothing but it is known as a direct form structure. Okay, so this structure requires total m minus 1 memory locations for storing the m minus 1 previous inputs, and has a complexity of m number of multiplication and m minus 1 addition per output point. As you can see this equation, in this equation it starts from k is equal to 0 to m minus 1. So what happened? So total that many multiplications we have to do between these two units, bk into z(2 minus k). So that is k is equal to 0 to m minus 1. So total values are m, and then we have to go for the additions of these terms because sigma sign is there. So additions are between first term and second term. So always you are getting the number of addition, that is m minus 1. So this thing we have mentioned over here. So it require m minus storing of m minus 1 previous inputs, has a complexity of m number of multiplications and m minus 1 additions per output point. So per output point it requires the m number of multiplication and m minus 1 additions. Since the output consists of a weighted linear combinations of m minus 1 past values of the input and the weighted current value of the input, the structure resembles a tapped delay line or transversal system. So if you compare that structure with the network, so you can say that, so whatever weighted linear combination you are getting, so that represent a tapped delay line or a transversal system. Tapped delay lines means for every tap you are getting some delay. So it is a tapped delay line or transversal system. So this particular structure is also called a transversal or tapped delay line filter. Okay, sometimes this direct form in your exam this will be given. Implement the following structure using transversal or tapped delay line filter. The meaning is simple. You have to implement that structure with the direct form realization. You have to implement that equation directly without any manipulation. Okay, so another alternate way here, this is the direct form structure we have seen in the previous slide. So here direct form realization of the FIR filter, whatever coefficients h0 to h of m minus 1, it is shown. But here you can notice here we are using the 2-bit adders. Okay, so here number of additions are more, as we have seen that total number of additions are m minus 1 if we are using the 2-bit adders. But instead of this 2-bit adders, if I replace this adder with the n-bit adders, what happen? We require only single addition at the end. Okay, so instead of doing this multiple additions, we can replace this 2-bit adders with this n-bit adder. So this is one alternate way to draw a direct form structure for FIR filter. Instead of 2-bit adders, we are using the n-bit adder, or you can say here m-bit adder. So that is, will add the values from h0 to h of m minus 1 and produce the same result y of n. Here you can compare that x of n first multiplied with h0, then added. Here h0, that is directly added, multiplied with h0 and then added. Second is x of n passed from this delay. Here x of n is passed from this delay and it is multiplied with the coefficient h1. It is multiplied with the coefficient h1 and then added. Similarly for all the coefficient and values. So this structure will produce the same results for the given input xn, and you are getting the same output yn. So here this is nothing but the direct form realization of the filter with two input adder circuit. Here structure changes only here multiple input or specifically M input adder to replace this 2-bit adders. So this is one alternate way to draw a direct form structure. Okay, now this is one simple example is given. So this is you can see y of n we are taking, that is h0xn plus h1xn n minus 1, h2xn minus 2, h3xn minus 3, and h4xn minus 4. So we have to draw the direct form structure for that, which is very easy. So h0x1, so x of n is multiplied with h0, we are getting the output. Then h1 n minus 1. When we are talking about n minus 1 means it is passed from one delay element. So x of n is passed from one delay element and multiplied with this h1 and then added. Then h2 xn minus 2. So here you require xn minus 2. So one more delay unit is added. You are getting the xn minus 2, which is multiplied with h2 and added. Similarly, you go for the next two terms, h3 and h4. So you are getting this y of n. So here you are applying the x of n. So this is known as a direct form structure implementation of the FIR filter, which is very easy to understand as well as very easy to implement. All of you got this? Anybody having any query? If you are having any query, please ask. Okay, so here we are shown this in the block diagram form. Same thing you can represent with the help of signal flow graph. Sorry, before to signal flow graph, one more thing is remaining. Let me cover this. It is a transpose form structure. Okay, transpose form structure means the transpose direct form structure is if we reverse the direction of all branch transmittances and interchange the input and output, the system function remain unchanged. So here whatever diagram you are shown over here, just a second, let me erase all the ink over here. Here this diagram is shown to you, x of n and y of n. Here what is written for this structure? To get the transpose structure, you have to reverse the direction of all branch transmittances. So whatever each branch transmittances are shown to you, you have to change their direction, and after changing their direction, you have to replace the or change the interchange the position of input and output. So your system function remain intact or unchanged. So here if you apply this change, here whatever direction you are applying over here, this transmittance direction you have to change. Okay, as you can see now here previous the flow from input to output, but now we have changed the or reverse the flow. So at the end what you have to do, you have to change this input or change the position of input and output. So here you have to write y of n and here you have to write x of n. Okay, so when you apply this structure, you are getting the same output. Okay, so here you are applying x of n and here you are getting the y of n by interchanging the input output position and changing the direction of branch transmittances. Okay, so let me show you that structure. So here you are getting this structure, x of n as an input. Here you are applying this changing. So x of n, first it is multiplied with h0, then added, and x of n multiplied with h1, and then it is delayed and added. Here x of n multiplied with h2, and then multiplied with z inverse to apply the more delay and added. So you are getting y of n finally over here. So this is nothing but to obtain the transpose form structure. The transpose form structure means you have to replace the input and output, and you have to change the direction or reverse the direction of branch transmission. So this is one alternate way to draw the direct form, or you can say implement the FIR filter in the direct form, but in the transpose way. Okay, now same thing is represented in this with the signal flow graph. So here for it is easy to understand from the signal flow diagram, that's why I drawn over here. So signal flow diagram of a direct form structure. So if I use the multiple input adder over here, so x of n it is passed from H0. Here this is nothing but adder, multiple input adder I am taking over here. And instead of okay, so H0 x of n multiplied with H0 added, it is delayed by 1 unit, then multiplied with H1, it is added. So here you are applying input and here you are getting the output. So this is nothing but the direct form structure representation using signal flow graph. Okay, now as we have discussed, to obtain what we have to do for the transpose form structure, we have to change the direction of branch transmittances. So whatever direction here you can see from left to right, here all the direction are changed from right to left. Okay, so when we change the direction from right to left, the direction is changed like this, and all the filter coefficient having the same value, only their direction of this branch transmittances are changed. When you change this direction, first is we have to apply this change, another is we have to replace the input and output. Here instead of x of n, you write y of n, and instead of y of n, just a second. Sir, please explain. Okay, in transpose form, let me explain this from this signal flow graph itself. Here I am applying the input x of n, and this is the signal flow graph representation. Okay, so H0, it is added over here, then x of n, it is delayed by 1 unit, we obtain the x n minus 1, it is multiplied with filter H1 and added. So here you can see that we are getting the y of n using this particular structure with the direct form implementation. Here I am using the multiple input adder to replace the 2 input adders. Okay, so in the transpose form structure, what happened? We have to replace the first we have to change the direction of branch transmittances. So whatever direction here you can see, if I say here left and here you are writing right, so here your direction are from left to right. For every direction you can say here directions are from left to right, and here for this case you can say the direction from up to down. Here you can say the direction from up to down. Okay, so this straight directions means whatever vertical transition, horizontal transition, they are from left to right. Whatever vertical transition, that is from up to down. So in the transpose, to obtain the transpose form structure, this is only the representation of the same equation. Okay, so what we are doing, we are changing this branch transmittances. So whatever branch transmittances or this direction, we are reversing that. Now here, whatever horizontal transition, that is now from right to left. You can notice over here, right to left. Okay, and whatever up to down transitions was there in horizontal, so vertical, so these are changed with the down to up. You can notice the changes over here. Okay, so when you apply these changes, this is the first change you have to apply to get the transpose form structure. Another is you have to replace, or you have to interchange the position of input and output. So here x of n is written, but here you have to write the y of n. Here y of n is written, so you have to replace it with the x of n. Okay, so this is how we will obtain the transpose form structure for the given FIR filter. Okay, I hope Ekta you understand this. So this is nothing but whatever FIR equation we have taken, this is the one alternate way to represent that equation in using direct form. Without manipulating the equation, we are just changing the direction of input and output and reversing the branch transmittances. So this is implementation of FIR structure, FIR filter. Okay, all of you clear up to this? Okay, so let me stop up to this for the transpose form structure. In the next lecture, we go for the cascade form structure. Okay, so we do one thing, just a second, I am stopping the presentation.